So now that we've talked about conjectures, we're going to do a quick reminder about quantified statements, because conjectures often take the form of a quantified statement. So if we have some open sentence P of X over a domain S, then we can use a universal quantifier on it to say for every X in a set in the domain, P of X. And so that means that it has to be true for every element in the domain in order for the entire quantified statement to be true. Now, on the flip side, there's the existential quantifier, and we can have there exists an element in the domain such that P of X is true. So to show that this is true, we just need a single example from the domain that makes it true. So I'm not going to take time to really talk through all of these examples because we've seen examples like this before. So here's one example. We can see that the universally quantified statement is false, but the existentially quantified statement is true. And I wanted to remind you also that if we want to show that one of these things is false, then we're basically showing that its negation is true. So the negation of the universally quantified statement, remember, is the existentially quantified statement of the negation of the statement P of X. So if I have the negation of for every X in the domain P of X, then there exists an element in the domain such that not P of X. And similarly, for the existential quantifier, if I want to show the negation of there exists an element in the domain such that P of X, well, the negation of that is for all of the elements in the domain, not P of X. So again, here's another example, taking a look at existentially quantifying it and universally quantifying it and finding that it's true one way, not the other. So here's where the real meat comes. So we've made conjectures, we can use quantifiers. Ultimately, in math, we want to find these conjectures, we want to come up with these conjectures, and they're going to be quantified statements a lot of times, and then we want to be able to test them. We need to test them to know if they're true or false, and then we're going to prove that they are true or show that they're false. So here we have an example. We want to prove or disprove that there's a real number solution of the equation x to the 6th plus 2x squared plus 1 equals 0. Now, most of our statements that we've looked at before have said either prove this statement or disprove this statement. Now our statements are going to say instead prove or disprove, and it's up to you to decide which one of those things you should be doing. So for the solution here, I can take a look at it and I can go, well, x to the 6th has to be positive, x squared has to be positive. I'm adding everything up, got a plus 1 there. So this is definitely not true. So in your head or on paper, you can test some values, you can figure out what you know about things, and you can decide if they're true or not. All right? So I come up with the idea that this statement is false, and so I need to show the opposite of this, the negation of it. So this is there is a real number solution, so this is an existentially quantified statement. So I need to show for every real number, it's not a solution to this. There's not a solution to this. So I'm going to take a real number x, generic real number, and I'm going to note that x to the 6th is greater than or equal to 0, and so is x squared. So then it follows that x to the 6th plus 2 times x squared plus 1 is greater than or equal to 0 to the 6th plus 2 times 0 to squared plus 1, which is greater than or equal to 1. All right, so that equals 1. So we've got this idea that x to the 6th plus 2x squared plus 1 is greater than or equal to 1. So there's definitely no way that it's going to equal 0. Here's another example. So I want to prove or disprove that x, y, and z are integers, then two of the integers have the same parity. I mean, think about this. Parity is even or odd, and there's only two categories that the three numbers can fall into, so I convince myself fairly easily that this is in fact true. Well, now I'm going to consider x and y. I'm going to take two of the integers to prove this and say, well, if they're opposite parity, then I need to do some more, but if they're the same parity, then the proof's complete. So let's say they're opposite parity. Well, then, without loss of generality, I can say x is even, y is odd, right? Well, then z has to be either even or odd. If it's even, then x and z are both even and have the same parity. If z is odd, then y and z are both odd and have the same parity. So the statement having three integers, x, y, and z, two of them have the same parity, is in fact true, and I've proven it to be so. Let's take a look at another one. So we're going to prove or disprove every even integer is the sum of three distinct even integers. Now, you hopefully can convince yourself that this is true fairly quickly, knowing that we've got negatives in play. So we're going to prove this true. So if you think about how you might prove something like this, well, it's really easy to add a number to 0 and get the number back. So ideally, we'd really like to be able to add two even numbers together, get 0, and then we just have to add the number to it. And in fact, in case 3, that's exactly what you see happening. So if the number is not 2 or -2, then n equals 2 plus -2 plus the number. All three of them guaranteed to be distinct since n is not equal to 2 or -2. Now, 2 and -2 were a selection of a positive and negative even integer that add together to become 0. I could have chosen any pair I wanted, but 2 and -2 it was. So I have the case where n does not equal 2 and -2 shown. So then all I have to do is show the case where n equals 2 and the case where n equals -2, and that I can do this. I can add three distinct even integers together to get these numbers, and I'm done. So it's easy enough to see that 2 equals -2 plus 0 plus 4, and -2 equals -4 plus 0 plus 2. So I can come up with these sums fairly easily for two integers, and then I can go with the general form for all of the rest of the integers. So we've talked about analyzing statements, and I've talked a little bit about where these statements might come from, but let's talk a little bit about how math is created. Math is a very creative process when we're developing new mathematics, discovering new mathematics. So creativity takes different forms for different people, but here's a really common technique that's used to come up with new mathematics. So a while ago, we showed that when a was an integer, if 3 divides 2 times a, then 3 divides a. Well, when we were doing that, we were so focused on proof techniques and being able to prove it, we weren't necessarily thinking beyond that problem. But you might have looked at that problem or might be able to look at it now and say, well, that's kind of interesting that that's true. So what else might be interesting about this? Well, it's usually interesting when we only have one direction of an implication to notice if the converse is true. And it is. If 3 divides a, then 3 divides 2 times a. That's true. So this could have been a biconditional statement to begin with. But that's not super illuminating, so it wouldn't be super exciting to mathematicians necessarily. There are other statements where the converse being true is an incredibly exciting thing. But in this one, that's not really the case. So we might be thinking, well, does it matter that the 3 is where it is and the 2 is where it is? Or could we switch it up and have this be true still? Or can we replace the 2 with other integers? What other integers can I replace the 2 with? If I put a 1 there, then this is super boring because it's 3 divides A, then 3 divides A. Obviously true. It's a tautology, right? All right. So what about if I put a 3 there instead? If 3 divides 3A, then 3 divides A. Well, that's not actually true, because if I plug in 1 for A, then I have 3 divides 3 times 1, which is 3. That's true. And 3 does not divide 1. So A equals 1 is actually a counterexample for this. So I know that there are integers that I can't put in place of 2, and I know that there are integers that I can, because I've got 1, I've got 2, and then I can see that it's true also for 4. So I'm trying to extend this result. I'm trying to generalize it even more than what we had. So I'm trying to rewrite it basically. If A is an integer, then if 3 divides k times A, then 3 divides A. I want to know what values of k is this true for. So what I really want is a set of values that are the possible values for k. So I want to rewrite this statement to be, for A an integer, 3 divides k times A. Whenever k is in this element S, that is my domain, then 3 divides A. So the question is, what is that set S? So we would be working towards what could be included in that set S. And even more ideally, what I'd really like is a set S that if the element is not in S, then the statement is not true. So I really want the set S that's true for this, but it's the complete set of values that this statement is true for. And in doing so, what I will have accomplished is a generalization. And it would read something like potentially A is an integer, then 3 divides k times A implies that 3 divides A if and only if k is an element in S. And all of a sudden we have a result that looks fairly different from what we had before. Now, this is great, and it would be a step towards developing new mathematics. And this mathematics has been developed, but this would be how you might develop new mathematics from that statement. Now, notice that 2 being the value for k is just an example of this generalization. It's a specific case of this generalization. And specific cases of generalized theorems are called corollaries. So we have this idea that when we have things that were results and they were theorems at one point in time, we might be able to generalize them enough that it makes that original theorem become a corollary of our more general and newer theorem. So get to creating.